Okay guys, let's go ahead and talk about our warm-up question, and then as I said, we're going to get into some notes today on some more free fall with some math practice as well. And then your homework for tonight is that your relevant application is due by 11:59 p.m. and then there is a My Open Math assignment that will be posted. It's not in there yet. Number one in the warm-up says, actually it's only one question, an object is in free fall for 5 seconds. Which of the following represents the motion of the object at each second? So we saw this yesterday. It's basically like that oil drop diagram. It's really a motion map without all the arrows on it, but it's showing the positions. So which one would show something that is falling? A, B, or C? B. Yeah, so again, when we have free fall, like A, this would be something you would have seen in our Unit 1. This object would be falling at a constant velocity because these are evenly spaced as they're going down. Sorry. B is going to show something that is speeding up as it falls because the distance that it is traveling with each second is increasing. And so we have a non-uniform change in our position. It's getting larger and larger and larger. Therefore, that's going to represent getting faster and faster. C would represent something that would be slowing down as it falls, so that's not something you would observe on Earth anywhere, really anywhere, because that's not how gravitational acceleration would work. So this would have to be some other type of scenario, maybe something like an elevator slowing down, coming to a stop. Okay. So again, important concepts, and this is a review from yesterday. Acceleration for objects in free fall is always negative 9.8 meters per second every second. Whether it is stated or not, you're going to be using that value in your calculation. So it's probably not going to be stated because it's the same number every time. So when you read a question, it may not be in there, but you need to know to use it. When an object is dropped or falls from an elevated height, the initial velocity is 0. I went over these things yesterday. They're not going to be explicitly stated in the question. It's not going to say an object is dropped from 0 meters per second. If it just says an object is dropped, or if it says an object is dropped from rest, you need to assume that that is 0. If it says an object is thrown, it's going to either give you an initial velocity or it's going to give you enough information to solve for an initial velocity. Okay, but your acceleration will be this value in all of our calculations. So this is the same image from the warm-up. It says, what is the acceleration of the ball at 4 seconds? Talked about this yesterday, so I'm just reviewing real quick before we go into our calculations today. What would be our acceleration at 4 seconds? Sorry? Negative 9.8. Again, that's the one that I said is kind of a trick question because it sounds like I'm asking for something other than that, but that's all I'm asking for. By the way, that's the acceleration at 0, 1, 2, 3, 4, and 5 seconds. Okay, so again, don't get tripped up by that. Again, when would this ball be moving fastest? Assuming this is all free fall. 5. Okay, be moving fastest at 5 seconds. So it'd be after 1 second, it'd be moving at 9.8 meters per second. After 2 seconds, 19.6. After 3 seconds, you add another one, but that's why we did 10 yesterday. 10, 20, 30, 40, 50. Okay, so yes, sir. When we're talking about free fall, if you didn't hear him, he said, wouldn't it reach a constant speed? When we talk about free fall, we're ignoring the fact that there is air resistance. So that is true. With air resistance, things will reach a constant speed, which is called terminal velocity as they're falling. But in all of our calculations, we are assuming that that air resistance isn't there, and therefore those objects will continue to accelerate. Okay, and then sketch the graphs. Again, we looked at this yesterday as well, but if we want to show something falling, our XT graphs pretty much always look like this. This is falling from rest and accelerating. And on my VT graph, falling from rest means I'm starting at the origin, and because I am falling, I'm going to put it in the negative region, moving away from 0. If for some reason you wanted to define the ground as positive, and then you could do that. It's arbitrary. I told you that I typically consider it to be negative, but as long as it shows something speeding up, you could also see these drawn in the opposite direction if you defined the ground as positive and anything falling down as a positive direction. But I don't typically do that, so my graphs are going to pretty much look like this. But I do want you to be aware of that in case you Google it and you see free fall graph that has a positive slope on the VT, that you could see that if they describe the ground as the positive direction. All right, so we're going to do a couple of practice calculations. because yesterday we were just kind of getting the hang of it. It's the same process though as all of the acceleration stuff. So this one, again, if you want to copy some of these down, I think we've got 3 or 4 of them in here. But this one says Luke drops a pile of roof shingles from the top of a roof located 8.52 meters above the ground. Determine the time required for the shingles to reach the ground. As a just best practice to help you get through these things, I'm going to recommend that you draw a diagram. They haven't been super important yet, but in this unit and in the next one especially, it's going to be very helpful for you to just simply sketch a picture. And I know I asked you to do that on the test, the last test, when I said draw a vector diagram. So it's the same kind of idea. It does not have to be pretty, okay? But you just need to have something where you can label all of that information in your picture. So here is my roof shingle dropping from a roof. Here is that 8.52 meters above the ground. Because it's dropping, my initial velocity is 0. It doesn't say it was thrown. And my acceleration is always going to be negative 9.8 meters per second every second. So again, just an object falling. You don't have to draw the roof. You just need to have that arrow here or the line here to label the height. And since I don't have an initial velocity, I can't really draw a vector, but if I did, I would draw a vector for that. Okay, and then we're going to use that same method, the guess method, where we label all of our givens and our unknowns so that we can find our equation and then substitute and solve. It's the same process we've been doing. So the given information in the question, and I put it in the picture, is that the displacement of these objects, this roof shingles, is going to be 8.52 meters downward. So I went ahead and put a negative sign. I'm going to define the ground as negative. Okay, my initial velocity is 0. Again, that's in the picture as well. Okay, and my acceleration is due to gravity, so it's negative 9.8 meters per second every second. The information I am being asked to solve for is time. So my unknown is time. So I have G and U in the guess method, given, unknown. And then my equation. So again, once you have done that, now you can turn and look at the list of equations that are still on my board. Hopefully they're also on your paper. If not, that would be a good thing to copy down. And you can determine which of these would allow you to solve for time. You know delta x, vi, and a. And so if you look at those equations, you're looking for delta x, vi, a, and t. And you're going to see that in the third one up on my screen. Or, well, here too, up on my screen. Okay, so delta x, vi, a, and t is going to show up in equation C. So that's the one you're going to want to use. Now, could you do this a different way? Yes. You are more than welcome to solve for final velocity and then time. That will also work, but the fastest way to do it in a single step is equation C. So this is the equation we're going to substitute into. Same information, it's a little rearranged. But I have now my equation on the screen. Substituting in, I have negative 8.52 equals VIT is 0 times t plus 1/2 AT squared. Again, this particular equation, I would not recommend using it to solve for time if your initial velocity isn't 0. Because if you try to solve for time and this initial number right here isn't 0, you will have to use the quadratic equation. Now, if you're really comfortable with that, cool, go ahead and do it. But otherwise, if you were in that situation, my recommendation would be to do it in 2 steps and to solve for final velocity first and then time. Up to you though. Okay, but this one's not an issue because this is going to go away. That's going to allow me to solve for time over here. I only have it in one spot. So I have negative 8.52 equals 0 t. I'm going to cross that off because that's going to be 0. Plus half of negative 9.8 is negative 4.9 times t squared. Again, to isolate my variable t, I need to get that negative 4.9 out of there. Currently, these are being multiplied, so I'm going to do it by division. Divide it on both sides, cancels it on the right, and now this is what goes on my calculator. But again, that's not going to give me my answer. That is t squared. So t squared is 1.7388, which means t is the square root of that value, which is equal to 1.32 seconds. Okay, again, same exact process as it was before in the last unit, okay, because this is still acceleration. So the difference is it's not going to list the acceleration. And if you read the question, a lot of times they're only going to give you one number because they're going to expect you to know if it says drop from rest, the velocity initially is 0. If it says that it's falling, your acceleration is negative 9.8. It's not going to print that in the question necessarily. Does anybody have a question about this one? Okay, let's look at another one. All right, so again, you're welcome to copy this one down as well. It says a stone is thrown downward at 5.2 meters per second into a deep well and is heard to hit the water 2.41 seconds after being thrown, it should say. Determine the depth of the well. Okay, so now we have an initial velocity. Okay, so you can have free fall with an initial velocity. It's not just dropping things, it's also throwing things down or up. Okay, so here is my picture. Okay, here's my stone. You don't have to have like it pretty, okay, but there's my stone. There's the time that I have in the question, and I'm looking for delta x. I could have also labeled my acceleration here because I do know what that is. But my given information, initial velocity is 5.2 meters per second downward. I'm going to go ahead and label that with a negative. I should have labeled that in my picture as well. Sorry about that. If you're drawing a picture, I would label that there. You can put it on this arrow. 5.2 meters per second. My time is 2.41 seconds. My acceleration is due to gravity, so it's negative 9.8 meters per second squared. And again, I am looking for the depth of the well, so I'm looking for delta x. Again, we're going through this process because it helps us to pick the correct equation. VITA and delta x, this looks a lot like the last one because we have the same things on the screen, so we're going to use the same equation. Delta x equals VIT plus 1/2 AT squared. Okay, again, you could alternatively with this information, VIT and A, you could use equation A to solve for VF, and then use VF to find delta x with either B or D. Like you could do that, but if you want to do it in one step, you're going to want to use equation C. Okay, so here is that equation, delta x equals VIT plus 1/2 AT squared. We're going to substitute into it. Negative 5.2 times 2.41, that's VI times T, plus 1/2, negative 9.8 times 2.41 squared. That gives me over here, these two numbers multiplied is negative 12.532, plus negative 4.9, that's half of negative 9.8, and then 2.41 squared is this number, 5.8081. I'm going to multiply these two values and then add them to this one, and I get this answer, negative 40.99 meters. So that would be the displacement of the rock. If I asked for the depth of the well, I would probably just say it's 40.99 meters deep. I wouldn't put the negative on it necessarily. That's just my displacement. Okay, does anybody have a question about this one? Again, I would recommend you copy these down or at least go through them with me, because y'all are going to have some to do on your own. I just wanted to go over examples of the three different types that you might encounter. So we have dropped, we have thrown downward, and now we have thrown upward. Okay, I forgot to turn on the animations here. Do that real quick. I thought it was on. Okay. All right, so again, if we are going to label, you can draw a picture like this one. Put the front somewhere. Okay, and this is supposed to be representing something thrown straight upward. It's just, if you want to draw that, you might want to still draw it looking like a little bit farther away. This looks more like a projectile. We're not actually looking at the horizontal motion, though. It's just up and down right now. And so we have thrown upward at 3.4 meters per second. What is the maximum height that it reaches? So again, you could label those numbers on here. I would put 3.4 meters per second right here. Okay, and I'm looking for this height. Okay, so obviously I'm given this. I have an initial velocity of positive 3.4 meters per second. What else do I know? Okay, what else do I know about this object? I heard one thing over here, but I'm looking for something else first. Acceleration. What is it? Negative 9.8. Okay, my acceleration is negative 9.8. Okay, the other thing that was said is the final velocity is 0. Why would we use that? Because if you throw something up in the air, guys, how fast is it moving right here?
0.
It's not. If you throw something up in the air, it slows down and it stops for a split second before it falls back down, right? So we know something about the object when it's at maximum height. And this question is asking, what is the maximum height? So we need to think, what do we know about this object at this position? And what I know is if I throw something up in the air, it's going to slow down, stop. Again, it doesn't stop for like 3 seconds like Wile E. Coyote in the cartoon. It's just an instant. But at that instant, it does stop, and then it falls back down and accelerates again. So I know that the final velocity at the top of that trajectory is 0. And guys, this is the hardest type of question to do because you have to, it's not given to you, you have to just know, oh, what can I use? What do I know about maximum height? Okay, and sometimes the question is not even asking about maximum height, but you can still use it to figure out the information that you need. So, again, this final velocity is at max height, and you might want to even write that, like top next to it, something. Okay, because it's not the end of it. I'll tell you about how we can do that in a minute if you want to use the end point. Okay, but VI, A, VF, and I'm looking for height, which means I'm looking for displacement. Okay, and so with this information, VI, A, VF, and delta X, if I look at my equations, which one should I use? A, B, C, or D? B. Okay, that one has VF, VI, A, and delta X. That's exactly what I have written on my screen right now, so that is the one that I would want to use to get this done in one step. VF squared equals VI squared plus 2A delta X. Substituting in, that looks like this. 0 squared equals 3.4 squared plus 2 times negative 9.8 times delta X. Okay, and so I'm going to do 3.4 squared, and then I'm going to subtract it over here. 3.4 squared is 11.56, and so I would have 11.56 plus this stuff. So I do want to move that over here. 0 squared, of course, is 0. Okay, but I get negative 11.56 equals negative 19.6. That's 2 times negative 9.8 times delta X. Okay, and so if I want to get this by itself, this right now is being multiplied, so I'm going to move it by division. I'm going to divide both sides by negative 19.6. And when I do that, negative 11.56 divided by negative 19.6 is 0.59 meters. So it did not go very high. Okay, anybody have a question about that one? Okay. Follow-up question. How long is the ball in the air? Okay, now I added this to my list of givens. That 0.59 meters that we just found. Again, I know that that's true for the top position. So these two things right here are true about the top of the trajectory that this object is taking. And so I can solve for the time it takes to get to the top because that's the information I have up there. Guys, if it takes, let's pretend that it takes 1 second to get to the top. How long is it going to take to get back down? The same amount of time. When you look at these trajectories, if you are at the same height, okay, if you launch from the ground and land on the ground, the time that it takes to get up to the top will be equal to the time it takes to get back down. Okay, so if we solve for the time it takes to get up, all we have to do is double it, and that'll give us the total time in the air. Okay, so again, this is the part that students get confused with. So I would definitely make some notes here with this example. And the last one. All right, the stuff that dropped and thrown down, that's pretty easy. This is the tricky one. Okay, so I'm looking for time. Here are my equations. I have everything that I would possibly need. I have VI, A, VF, and delta X, so I can solve for time with any equation that has T in it, which means I could use A, C, or D. Now, I wouldn't really want to use C because then I have to do the quadratic. So it's really A or D, up to you. I think I used A. Okay, VF equals VI plus A times T. And so if I substitute in, that is 0 equals 3.4 plus negative 9.8 times T. Subtract 3.4 from both sides. And I have negative 3.4 equals negative 9.8 T. And then divide by negative 9.8. And I get 3.4 divided by 9.8. My time up, T up, is 0.347 seconds. Again, that's just the time to get to the top. So what do I have to do now? Times 2, or add it to itself, however you want to think about that. But time up plus time down will give me my total time. And so if I double that, I get this. The total time is 0.694 seconds. Okay, so again, these are the tricky ones. And this is, by the way, what you're going to have to do in the next unit as well. Okay, so again, I would write somewhere on your paper, time up equals time down. And you might also want to make a note about what you know about an object at the top of its trajectory. At the top of its trajectory, we call that max height or peak height. Okay, you know that the object has a velocity of 0. It stops moving for an instant before it falls back down. Okay, so you know that about max height, the velocity is 0. And you know that at the time it takes to get there is half of your total time. Okay, so you know those things about that height, which is going to be important to help you solve any calculations with a thing thrown up in the air. Technically, this is a projectile. So with a projectile thrown straight up, okay, but an object in free fall. Okay, same scenario. It says sketch the xt, vt, and at graphs. If I want to show this motion, and I talked about this yesterday, on my xt graph, I need to show something that is going upward and slowing down, turning around, and then going downward and speeding up. And so you're going to have that. Okay? If you have an object thrown up in the air, you're going to have a parabola. It's going to look just like the trajectory of the object, really. The velocity. Again, the velocity of this object initially is positive because it's going up, but it slows down to 0. So I'm going to have it start in the positive region and slow down to 0, and then it's going to go in the negative direction and speed up, and so it's going to look like that. Okay, if an object is thrown upward and changes direction, this is what the VT graph will look like. Where does it change direction? Yeah, when it crosses the x-axis, right there. Okay, so I will ask you that question, so just be aware of it. Okay, and then my AT, every time, and I said this yesterday, they will all look exactly the same. It does not matter if it is thrown upward, thrown downward, or dropped. Acceleration is always gravity. Gravity is always negative 9.8. All of those graphs will look like that. Does anybody have a question about the graphs? Yes?
For xt, will we always draw it like that, even if it says, like...
If it is dropped from rest, no. If it's dropped from rest, you're just going to have basically half of it, and it's just going to be this half over here.
But for that one, if we didn't have the picture showing that it came back down, do we just assume that it, like, went up and stopped, or do we assume that it came back down as well?
If something's thrown up, you would want to show it coming back down, yeah. If I said draw the graph for an object thrown upward until it gets to max height, then yeah, you'd just draw the first half of it, but I don't think I would do that.
Okay.
But if I did, sure. All right, one last thing I want to talk about. The velocity time graph shows data for a penny falling from the observation deck of the Empire State Building in New York City. How far has the coin fallen after 4 seconds? And if the observation deck is 320 meters high, how long will it take the coin to hit the ground? Okay, so now I have a graph. This is a VT graph. How can I find how far something falls from a VT graph? How do I find displacement on VT graph? Area. Okay, same thing as before. The area is this triangle right here. Okay, so all you would have to do is find the area of that triangle, 1/2 base times height. Base is 4, height is negative 39.2, and so it'd be 1/2 4, so 2, times negative 39.2, and that would give you, I thought the answer was on there, that would give you the answer here. So let me go ahead and do that. Okay, so the displacement is negative 78.4, which means it would have fallen 78.4 meters after 4 seconds. Okay, again, you would just find the area. Again, you're going to see that on the test as well. If the observation deck is 320 meters high, how long will it take to hit the ground below? Well, again, you can see here that the slope of this line is the acceleration, and the slope is negative 9.8. After 1 second, it's at negative 9.8. After 2, negative 19.6. Again, they're all going to look like that, although it may round to 10. It may be 10, 20, 30. But again, this is just a straightforward calculation. So if you'd like to try this one just for some extra practice, you are welcome to. I don't have it worked out up here, but I will work it out and I can check it for you if you like. However, what you might want to look at instead, because it is due tonight, is your RA. Okay, so for the remainder of the class period, which is a little shorter since we're on advisory schedule, but you guys still have about 15 minutes. You can open up that RA and make sure that you have it all the way completed because it's due by 11:59 p.m. tonight. That would be my recommendation to start there. That homework assignment in My Open Math isn't due till tomorrow, so I would definitely focus on the RA first. But I will get that other one posted as well. So again, if you'd like to try this one, I'll go ahead and solve it. You're welcome to ask me to check yours, I will. Otherwise, you can work on your RA, or, I want to mention this as well. There is a unit summary posted in Schoology for this unit. However, I was not able to actually put it in the form that we've been using in a sheet, so it's just a Google Doc. There will be an answer key posted because it's not going to check your work for you, and I do want you guys to have the answers, but that would be another thing to look at if you want to do any more practice with the math or the graphs or anything else, because guys, what we talked about today and yesterday, that's it. That's this whole unit. It's really just an extension of the last one. So you'll have tomorrow to work on some practice. I'll probably go over just a few more with you, but you'll have that tomorrow's class period pretty much to work on those practice problems that are in my open math. So I'm going to stop talking. I'm going to let you guys open up your RA, ask questions if you have them. I'm going to get an answer to this one. If you want me to check it, let me know. And then, again, don't forget to turn in your RA tonight by 11:59 p.m.